Hello, and welcome to my video series of algorithms. This is part 2 of Module 5, Divide and Conquer Algorithms. In this video, we will explore the counting inversion problem. Imagine you are running an online business and you want to build a product recommendation system. For example, when a customer types in buy fruit, your system should return a list of fruit products ranked by the likelihood of purchase. If your system predicts that the customer prefers grapefruit the most, it should rank grapefruit the first. This approach can satisfy our impatient customers and expedite the transactions. Now, a question arises: how do we evaluate the recommendation system? Well, we can collect retrospective data, such as the click rates of the recommended items among similar customers, and compare the click rate ranking with the recommendation ranking. For instance, if the system recommended grapefruit first, and most customers actually click on grapefruit, it is a positive indicator. However, if most customers actually click on tangerine instead, we need to adjust our recommendation system accordingly. In this case, we are given two rankings. The first ranking is based on actual click rate. Here, we observe that most people click on tangerine, followed by grapefruit, and mango the last. The second ranking is the recommendation ranking. In this ranking, the system lists grapefruit first, mango second, and tangerine third. To compute their similarity, we treat the click rate ranking as the reference or ground truth. In other words, the click rate ranking is considered to be in order. Thus, the number of out-of-order pairs in the recommendation ranking can serve as a measure of similarity. For example, because the system recommended tangerine third and grapefruit first, while in the reference, tangerine is first and grapefruit is third, they form an out-of-order pair, or an inversion. Similarly, tangerine and mango also form an inversion in the recommendation ranking. Together, we have two inversions in this example. Intuitively, the more inversions they contain, the less similar the two rankings are. Know that one of the input ranking always serves as the reference and is in order. Therefore, we can reduce the amount of input by mapping the second ranking to the reference. For example, the second column shown here will always be 1, 2, 3 because it is the reference and always in order. The numbers in the third column are the mapped ranking of the fruits to the reference. The mapped ranking alone combines information from both lists, and the number of inversions can be obtained solely from the mapped ranking. Now, we can define the counting inversion problem. Given a list of numbers, count how many inversions are in it. We can easily construct a naive solution to the problem. Simply check every pair of numbers and determine whether the pair corresponds to an inversion. This method results in a time complexity of O(n) squared, where n is the length of the list. Is it possible to devise a faster algorithm? Know that sorting and counting inversions are closely related problems, as sorting is essentially a process of rectifying all inversions. Given that sorting can be done in O(n) log n time, we postulate that counting inversions can also be done in O(n) log n time. Recall that we showed how to reduce the time complexity for sorting from O(n) squared to O(n) log n using divide and conquer. Here, we want to do the same for counting inversions. As discussed earlier, the design of a divide and conquer algorithm should focus on its divide and merge steps. We also need to keep track of the time complexity of the divide and merge steps to verify that they are faster than the direct solution without divide and conquer. First, the divide step can be done in linear time O(n), as we can simply make copies of the input into partition 1 and partition 2. For the merge step, we observe that the total number of inversions can be computed as the sum of the within partition inversions and the between partition inversions. In the example shown here, the within partition inversions are indicated in black, and the between partition inversions are indicated in red. You can verify that their sum is indeed the total number of inversions in the entire list. Now, can we obtain the within partition inversions? Yes, because we can count them using recursive calls. The challenge is how to count the between partition inversions. Naively, we can compare all pairs of between partition numbers, but this approach will still require O(n) square time and would not lead to a faster algorithm. Now, recall the close relation between sorting and counting inversions, where sorting essentially rectifies all inversions. For the merge sort algorithm, it corrects the between partition inversions in its merge step using linear time. Therefore, we should be able to modify this merge step and count between partition inversions as well. Under this intuition, we show how to combine both procedures and develop an algorithm that simultaneously sorts the numbers and counts the inversions in linear time. Before we discuss the details, I recommend reviewing the merge sort algorithm if you are not familiar with it. I will put the link for merge sort in the description. Now, let's go over the procedure using a simple example shown here. Since we are modifying the merge sort procedure, we can assume that the numbers in the two partitions are sorted, which will help us count inversions faster. First, note that partition 1 contains the first half of the numbers from the input, corresponding to the items that receive higher rankings in the reference. Likewise, the items in partition 2 receive lower rankings in the reference. As a result, if we need to push a number in partition 2 into the merged list, then the number will form inversions with all remaining numbers in partition 1. This is because the number is in partition 2, meaning that it is ranked after all elements in partition 1 in the reference list. Meanwhile, since we are pushing the number to the merged list, it means that it has a smaller value and is ranked higher in the second ranking than all remaining numbers in partition 1. Together, they match the definition of inversion. So, the pushed number from partition 2 forms inversion with every remaining number in partition 1. Now, we can detect these conditions while performing the merge procedure of merge sort. Recall that the procedure assigns two pointers and have them point to the first numbers of the two input lists. It compares the numbers that are being pointed and pushes the smaller one to the merged list. It then moves the corresponding pointer to the next number and repeat the process until both lists are exhausted. In the example shown here, we find that 1 in partition 2 should be pushed to the merged list. It implies that the item is ranked first in the recommendation system and has a smaller value than all remaining numbers 2 and 4 in partition 1. However, it is in partition 2. It is ranked in the lower half in the reference. Thus, it forms two between partition inversions with all remaining numbers in partition 1. We then add 2 to our between partition inversion counter. Next, the number 2 from partition 1 is smaller and will be pushed to the merged list. This indicates that the corresponding item is ranked second by the recommendation system. Since it is in partition 1, which means that it is also ranked in the first half of the reference ranking, it will not form any between partition inversions. In the third pass, the number 3 from partition 2 is pushed into the merged list. Similarly, it forms a between partition inversion with the remaining number 4 from partition 1. Therefore, we add 1 to the between partition inversion counter. Finally, the number 4 from partition 1 is pushed into the merged list. Since it is from partition 1, no between partition inversion will be added. As we have finished traversing both partitions, we terminate the merge step. We recorded 3 between partition inversions in total, matching the result obtained using the brute force method. As expected in this process, we both counted the between partition inversions and rectified them by producing the merged sorted list. The sorted list, along with the number of between partition inversions, will be returned to the upper level recursions. We name the process merge and count and summarize its pseudocode here. We mark its main difference with the merge process of merge sort in red. Specifically, in line 3, we assign 2 counters, N1 and N2, to keep track of the number of remaining elements in the 2 partitions. In lines 6 and 7, we need to update both counters accordingly. More importantly, in line 7, we add the remaining number of elements in partition 1 as the number of between partition inversions if necessary. This is the pseudocode for the divide and conquer algorithm for counting inversions. It is also very similar to merge sort, except that it needs to return both the sorted list and the total inversion count. Note that in line 7, the total inversion count is computed as the sum of within partition and between partition inversion counts. Finally, the time and space complexity for counting inversions are also the same as merge sort. This is because we only need to add a few scalar variables to keep track of the number of remaining elements in the partitions and store the inversion counts. Additionally, computing these scalar variables can all be done in constant time. Therefore, it retains the original time complexity of merge sort. Note that this time complexity is faster than the ON squared time complexity of the naive approach. In summary, we have discussed the counting inversion problem and provided a divide and conquer solution in this video. Essentially, we modify the merge step of merge sort such that it can merge the 2 input partitions and count between partition inversions at the same time. The resulting algorithm runs in ON log n time and ON space. Thank you for watching and see you next time.